Hello, everyone, and welcome to Chapter 3 of Flight Physiology and Human Factors. In this chapter, we are going to actually examine the discipline and the study of human factors, break down what that actually entails, why we concern ourselves with the human factors involved in flying an airplane, and we'll tie a lot of important points into some of the things that we learned in the first two chapters. So our chapter objectives here are, number one, to understand the purpose of the human factors discipline, bearing in mind a lot of what we learned in those first two chapters, that number one, most aircraft mishaps are going to be the result of inevitable but manageable human error. So we learned in chapter 1 that human error is responsible for about 80% of all aviation mishaps, and we learned in chapter 2 about the different types of errors and mistakes and violations and slips and lapses that can occur by a person that is flying an airplane. And we have to understand that error is inevitable. We are human. We are limited in our cognitive capabilities, our skills, our motor controls. So we have to accept that error is inevitable. But what we also learned in chapter 2 is that by having an organizational and systems approach to how flight operations are managed, we can ensure that one error or one mistake is not going to crash an airplane. So we can manage our error and minimize their impact when they occur. Number two, we want to define the subdisciplines of human factors, which are going to include physiology, which is going to be really the main focus of this class as we move into chapter 4 coming next week, but also psychology, ergonomics, and anthropometry. And then finally, in this chapter, we want to obtain a holistic appreciation for the limitations of physiological and cognitive function. Again, we are human. We are only capable of so much. Give us enough time, we're going to make some mistakes, right? So we want to take that and keep that in mind. And as we move forward in this class, we want to prepare ourselves to learn the basics of physiological and cognitive function in each of the coming chapters. Okay, so as we learned in chapter 1, aircraft accidents have become, over time, as the aviation industry has advanced, they've become more an issue of pilot error as opposed to mechanical failure. So as you can kind of imagine, when flying an airplane was a brand new concept, there were lots of design failures. There were mechanical problems. There were engines going out. There were lots of airplanes crashing, not because of the skill of the pilots involved, but because the aircraft was not poorly designed or had some sort of aerodynamic flaw or something like that. Well, as we learned at the end of chapter 1, the technology of aviation, aerodynamics, lift, reducing drag, and all those sorts of things has gotten better and better and better and better. And what we know about technology is that those things are going to continue to get better and better and better and better as time goes on. But human capabilities have not really improved in that time. So that has kind of flipped the switch where, okay, well, airplanes are still going to have accidents every now and then. I mean, thankfully, we live in an age where aircraft incidents and accidents are very rare, but when they do occur now, overwhelmingly, it's going to be an issue of operator error more so than mechanical breakdown. So pilot error has always been a problem. It's just we didn't really notice it that much in the past because of all those mechanical failures. So if you kind of look back into what your textbook talks about with World War II pilots, and I think I mentioned the novel Unbroken in a previous video, aircraft would get lost all the time because of these mechanical breakdowns. But again, that doesn't mean that pilot error hasn't been a thing. So let's take one example of this. A common occurrence for pilots in the past was a understandable issue of selecting the wrong lever or switch when trying to operate controls within the aircraft. So the example given by the textbook is things like the landing gear or the flaps, two things that are going to very commonly be operated when you're either taking off or landing, which, again, we learned in Chapter 1, those are two of the most dangerous aspects of any flight operation. Well, so the way it apparently used to be is that the knobs and levers and switches for things like the landing gear and the flaps used to be indistinguishable from one another. And what's worse, they used to be located right next to each other. So if a pilot is executing a landing procedure and is coming in on approach, if the pilot means to hit the flaps but instead hits the landing gear or vice versa, that's going to disrupt the landing procedure and potentially lead to a undesirable aircraft state. Well, so this became kind of an issue. So this put a lot of pressure on the pilot to be perfect in every phase of the flight. Make sure that you're always flipping the right switch. Make sure that you're always turning the right knob. Make sure that you're always doing this correctly, doing that correctly. This was a perfect example of the aircraft not being designed with the limitations of the human operator in mind. So thankfully, this gentleman, this psychologist, Alphonse Chapanis, came along, and he really revolutionized aviation by taking a psychological approach to aircraft design. What this guy did was he took these flight controls and he added these little attachments to the switches and valves and knobs to make sure that the pilot had a kinesthetic and ergonomic connection to what switch they're actually flipping. So this allows the pilots to make this psychological connection between what they feel and what they see to what the function of the switch actually is. And in this figure here from your textbook, you can kind of get the feel here. So this attachment to the flap control knob is actually kind of thin and resembles the flaps on the wings. The landing gear switch actually has a little attachment that looks and feels like a wheel. And you can see kind of some similar things for the thrust control, the mixture control knob, and other things like that. So this reduces the likelihood that when a pilot grabs a certain switch or tries to flip a certain knob, that they're going to mistake that for something that it's not. So because of the way these things actually feel when you touch them, that actually causes there to be a hardwired set of communications happening between your hand that is trying to operate the knob or operate the switch, your brain, and then back and forth again so that you can make an educated and hopefully mistake-free assumption as to what switch you are about to flip. So doing this by this Chapanis fellow, this greatly reduced these incidents of pilots flipping the wrong switch because it felt or looked exactly like another switch. So if that's not enough to convince you as to why we need this human factors discipline for us to study, think of it in kind of a more historical context. So when we entered into World War II in 1941, we obviously were fighting in the Pacific theater a lot. So we were having to fly very long distance missions between California and Hawaii and different islands that were controlled by the Japanese Empire. And then if you're talking about the Atlantic theater, same thing. We were having to fly these long distance missions from our bases in England and then Germany or Italy. So World War II really saw this need for American fighters and bombers that traveled faster, had longer ranges, and can outmaneuver enemy aircraft while also holding very heavy payloads of munitions. So the deal with this, though, even though the technology advanced to the point where we could actually accomplish these things, the downside is that the more capable aircraft became, this drastically increased the strain on the pilot and further minimized the margin for error in flight. So this really placed a premium on extremely skilled pilots that made as few mistakes as possible. And as we learned in the previous two chapters, well, mistakes and errors are going to happen. So Definitely not the right thing, not the right approach for us to too rapidly increase the technology of the aircraft without considering the human operator in mind. So we finally got to the point where we recognized the defined limits of the human body and have since then sought to design aircraft with the human pilot in mind. So if you go back to World War II, again, lots of airplanes were crashing, not in combat. They weren't getting shot down in dogfights. A lot of aircraft were crashing because of the pilots not really being able to keep up with these technological advancements. So the airplanes were not being designed with the pilots in mind. So a lot of aircraft being lost in training missions in preparation for combat rather than in combat itself. And again, if you're interested in this, I highly recommend the book Unbroken. So, of course, errors are still going to happen, but again, this is why we can be thankful for the human factors discipline. Modern airplanes are designed with the human operator in mind so that we can minimize the severity and the implications of some of these errors when they occur. So, a lot of our focus in this class and on human factors is going to be on our study of the actual physiology of the human operator of the aircraft. We want to know how our brains work, how our hearts work, how our sensory organs work, how we interact with the unique atmosphere that being in an airplane puts on us, but we also want to consider the flight environment as well. So as you can see in table 3.1 here, the flight environment consists of a physical side, which not only considers the actual aircraft itself, but also issues like maintenance, what the aircraft is capable of in terms of airspeed and altitude limitations, airworthiness. We can also consider things like the weather outside, the temperature, the humidity, what time of day are we flying in VFR rules or IMC conditions? Are we flying in mountainous areas? Are we flying over the ocean? Things like that. There are operational things to consider, such as FAA regulations, your own airlines procedures and things like that, company requirements. And then like just the regular things like pre-flight checklists, any manuals or checklists that you go through when you are in the middle of your flight operations. And then finally, you have the social flight environment, which consists of all of your interactions with other people, not just the people in the flight crew, like your first officer, your flight engineer, and I know flight engineers aren't really that much of a thing anymore, but trainers, maintenance workers, dispatchers, air traffic control, the people who schedule the flights, your cabin crew, your stewards and stewardesses, the ground crew. So your interactions with not only the physical aspect, the regulatory side, and then the people side, these all make up the flight environment, and they are worth considering as well. But again, a lot of our focus is going to be on actual human physiology. So what you should take from this is that the human factors discipline is actually very much multidisciplinary. There's lots of things that fall under what we'll call the human factors umbrella, but our focus is going to be on these. Physiology and medicine, that's probably going to be 70 to 80% of what this class is. Anthropometry, which we'll get to in just a second. Cognitive psychology, and social psychology. So let's take a look at each of those individually. And before we hop into physiology and medicine, let's look at anthropometry first. So anthropometry is the study of the size and shape of the human body and how it affects its interface with the environment. So specifically what we're talking about here is how big and how shapely is a person and how does that affect their ability to fly an airplane? So what your textbook has to say about this is that historically, the military has, maybe without meaning to, discriminated against some people based on how big they are or how small they are. So historically, the military has designed their aircraft to only accommodate about 90% of the possible people in the population. So what that means is that some people are too tall to fly an airplane and some people are too short. So the aircraft and the flight deck is designed with an average person in mind. So the reason why we're going to concern ourselves with this part of human factors is that it stems from the necessity of the entire flight deck comfortably accommodating the pilot so that they can not only see out the cockpit windows if you're flying VFR, but that they also have easy access to all of the flight controls. So your textbook also mentions the tragic case of the singer-songwriter John Denver, who was flying his own custom airplane, which was designed in a fairly poor way that didn't allow him to access his fuel regulators, which were up, like I think, behind his shoulder, and that was a major contributor to his crash. So anthropometry is going to consider not only the size and the shape of the person, but to make sure that the flight deck and the aircraft is designed so that every one of the essential flight controls is within easy access with your hands. So I mentioned the military kind of having a specific way of designing their aircraft before, but modern aircraft are thankfully specifically designed with the anthropometric characteristics of the pilot in mind. Make sure they're comfortable, make sure they can see, and make sure they can reach all of the controls. So if you've ever worked in an office environment, you've probably seen a figure like this. You'll often see these kind of ergonomic design diagrams in modern computer workstations. So modern computer workstations are designed to minimize the risk of musculoskeletal injury in office workers. And if you're running a company that has lots of office workers, you can obviously see the benefit here. If you can make sure that all of your office workers are comfortable in their working environment, you minimize the risk of your workers having to take time off because they have hurt their back or hurt their wrists while working at the computer. So we're not going to spend too much time on that because we're not considering working at a computer. We're talking about flying airplanes, right? But very much the same principles can be applied to pilots. So we need to have the flight deck and the seat and everything designed so that the pilot sits in the design eye reference point, which is what I was mentioning before, which is the pilot orienting his head and his eyes in a space that is optimal for which the pilot has maximum visibility and maximum access to all of the flight controls. Okay, so let's move on to human physiology and medicine. So I've talked about physiology before. This is the branch of biology that focuses on the study of body function as opposed to something like human anatomy, which focuses on body structure. So we are very much going to concern ourselves with human physiology in this class at a basic level, but we will see a little bit of anatomy. So what I tell my physiology students all the time is, yeah, this is a physiology class, but anatomy is just the opposite side of the same coin, so we can't very well ignore it altogether. So as you learn some basic human physiology, you're going to learn how the human body and its different organ systems operate under normal, healthy conditions, at least in the way that is relevant to flying an airplane. So medicine is basically an application of physiological knowledge that is used to treat disease. Another thing I tell my physiology students all the time is that the reason why we study how the human body works when it is normal, when it is healthy, is so that we know exactly how these things are supposed to work, and we can pinpoint exactly which component is not working properly when a patient presents with a particular disease. And disease is just the breakdown of normal physiological mechanisms that result in abnormal function, health, and comfort. Okay, so for flight physiology for this class, as future pilots, you're going to be less concerned with treating diseases or figuring out which prescription drug to give somebody, obviously, as you will the unique way the human body functions in an aviation-specific environment, such as high altitude, low pressure, and low oxygen. However, that is not to say that medicine is irrelevant here. So somebody's medical condition can absolutely affect the way that they interact with their flight environment. So for example, pre-existing disease conditions like heart disease, high blood pressure, poor eyesight, infectious disease, having a cold or something like that, these can adversely affect flight operations. as can external stimulants or depressants like alcohol, drugs, and an altered psychological state. So let's give ourselves an example here of a flight environment issue that affects human physiology and vice versa. So this is something that we're going to cover extensively in chapter 4, which is what we start next week, but we'll go ahead and kind of give a primer here so that you'll be prepared for that. So as an aircraft gains altitude, the atmospheric pressure is going to drop. So the atmospheric pressure is basically the density of the gases that are all around you. So the higher you get in the atmosphere, the thinner and less dense the air becomes. And a consequence of that, since the oxygen that we need to leave is in the air that we breathe, the partial pressure, or basically the percentage of the air that's made up of oxygen, is going to drop as well. So physiologically, the reason why this is relevant is because all the cells in your body, of which you've got 30 to 40 trillion different cells in your body, especially your brain cells, they require a very steady and unceasing supply of oxygen in order for them to function properly. This is why you have to breathe. You have to keep breathing to stay alive, because otherwise your cells will not be able to make enough energy for themselves. When cells get the oxygen that they need, they are able to efficiently harness the energy out of the food that you eat. If you stop breathing and you stop getting oxygen, your cells will not be able to harness that energy anymore, and they will no longer be able to function, especially your brain cells. Your brain cells need oxygen arguably more than any other part of your body. So hypoxia is the physiological condition of a tissue, organ, or the entire body not receiving an adequate supply of oxygen. So the reason why high altitude is an issue here is because if you are at high altitude and you are not in a pressurized cabin environment, every breath you take is going to supply your body with a lot less oxygen than you otherwise would be if you were standing on the ground. So that is something that we are going to study very carefully when we get to chapter 4. What is oxygen? Why do we need to breathe it? And why does flying in an airplane present potential problems for us in terms of hypoxia? So to explain this a little further, because of the drop in the partial pressure of oxygen as altitude is gained, roughly above flight level 100, so that's 10,000 feet, any pilot's crew or passengers must either be supplied with supplemental oxygen, or you have to exist within a pressurized cabin. So in a minute, we'll talk about some of the history behind how we've made advances in this and how we've learned about hypoxia and why you need to take special precautions when flying above 10,000 feet in the atmosphere. So some symptoms of hypoxia include, but are not limited to, fatigue, tachycardia, which is an excessively high heart rate, cyanosis, which refers to the blue coloration of the skin, which again is a symptom of not getting enough oxygen, and then loss of consciousness. So loss of consciousness is the real big key issue here. If you are a pilot flying an airplane and you get hypoxic and you lose consciousness, that is very, very bad news. You are considered incapacitated and no longer capable of flying your airplane. So hypoxia is deadly serious business, and when we get to chapter 4 next week, we are going to make sure that we do our due diligence talking about it. So this is something that I'll mention again when we get to chapter 4, but just a quick little case study in hypoxia. We're going to consider the 1999 Learjet crash that happened in South Dakota. This flight, which was transporting, among others, pro golfer Payne Stewart, crashed after cruising across half the country. The flight was scheduled, I believe, to go from Florida to Texas, but somewhere along the way, as the flight reached cruising altitude, apparently the plane just kept gaining altitude. It did not make the turn southward towards Texas, and radar operators took notice of this and scrambled some F-16 fighter jets to go check on it. And the pilots of those fighter jets reported that they could not see any movement in the cockpit or in the window or in the passenger side of this Learjet. And they surmised, they had no like firm evidence, but they guessed that everyone on board was incapacitated, likely because of hypoxia. So what would cause hypoxia here? A Learjet is a type of aircraft that should have a cabin pressurization mechanism. So our best guess here is that the cabin experienced rapid depressurization, and this exposed the pilots and the passengers to the low partial pressure of oxygen which is present at high altitude, and everyone very quickly developed symptoms of hypoxia and likely lost consciousness. So this airplane was basically on automatic pilot at this point, and it just kept gaining altitude and kept flying across half the country with every person on board completely unconscious, and they have completely succumbed to the effects of hypoxia. So another thing we can speculate here is that the effects of hypoxia happened so quickly that the pilots passed out before even realizing what was going on. This is why a lot of training in becoming a pilot involves understanding how your own body responds to hypoxia so that you can be aware of the signs and the symptoms of it before you lose consciousness. So the pilots clearly in this case were not quick enough to get themselves supplemental oxygen before they became incapacitated. So very sad case. That flight did end up crashing somewhere in South Dakota. I think it reached almost 50,000 feet in altitude before it eventually ran out of gas and then did a death spiral and crashed in South Dakota. Very sad incident in aviation history. So let's talk a little bit about the history of physiology in aviation. And you're going to see a lot of this relates to altitude, oxygen, and hypoxia. So 1875, this obviously predates the use of airplanes, but airplanes weren't the only way to get up in the air at that point. We did have hot air balloons at this point. So in 1875, 3 French aeronauts, I kind of find it funny that your textbook decides to depict them that way. I mean, I guess their names aren't important, just 3 French aeronauts. So anyway, 3 French aeronauts seek to break James Glacier's altitude record of 36,000 feet in a hot air balloon. So these French aeronauts decide they're going to climb into a hot air balloon and they're going to fly even higher than 36,000 feet. Now, here's the funny thing. They did at least have an understanding of the fact that they were going to need to bring oxygen with them. So they weren't completely in the dark in that regard, but they were actually warned ahead of time that, hey, you're not bringing enough oxygen. You're going to need a lot more oxygen than what you're bringing. And that ended up being the case. And they only made it to 28,000 feet before succumbing to hypoxia. Remember what I told you. You need supplemental oxygen everywhere in the atmosphere above 10,000 feet. So it's actually kind of amazing they made it 18,000 feet above that limit before succumbing to the effects of hypoxia. Fast forward about, looks like about 40 years or so, Wiley Post, if you're a native Oklahoman, you'll recognize that name. There is an airport in Oklahoma City named after him. Wiley Post flew while wearing a pressure suit, and he was able to make it to 50,000 feet. And this was effective in combating the effects of hypoxia and decompression sickness. So again, when you fly at that high of altitude, you're not just dealing with a lack of oxygen, you're dealing with a general lack of air pressure. And these are all things that we're going to learn in chapters 4 and chapter 5. So just kind of an appetizer for you for right now. Fast forward another 11 years, Captain James Doolittle conducted the very first blind flight by conducting a flight totally on instruments with no visual references at all. So was never able to see outside the airplane, operated and conducted a safe trip flying his airplane without any visual references, flew totally by instrument, and this paved the way for what we consider to be all-weather flying. So this basically tells us that it is possible to rely solely on instruments, and you don't necessarily need your sensory inputs that you process through. As we've established, your entirely error-prone and limited human body. And then as we make our way into the 1940s and World War II, the U.S. Army and the United States Air Force both introduced physiological training regimens for pilots to educate and arm them against the stresses of not only high gravity, but also the effects of altitude, hypoxia, and spatial disorientation. Now, certainly we still had lots of non-combat related airplane crashes here, but again, we talked before about how some of that is due to mechanical issues, but of course, a lot of that is due to human error as well. Okay, so moving on to psychology, you, I'm sure, are aware of psychology, so this is just the study of the human mind and behavior. Our focus is going to be on the specific function of the human brain and its influence on behaviors that both positively and negatively impact flight operations rather than so-called psychological disorders. We're not here to be able to recognize depression or to recognize things like schizophrenia or anything like that. So psychological abnormalities have been shown to play little to no role in the history of aviation accidents and incidents. So the idea that someone who is psychologically disturbed is going to fly an airplane and then do something like intentionally crash it, that kind of thing happens so rarely, it's hardly even worth talking about in our discussion of psychology. So here we can actually see a major breakdown of some of the major branches of psychology that are applicable to aviation human factors. So we, of course, have things like behavioral psychology, which is going to be the study of observable human behavior and how it applies to aviation. So this is basically going to kind of be the solid foundation upon which we not only talk about behavior itself, but the actual function of the human brain and how we perceive our sensory inputs that are necessary to actually fly the airplane. So same thing goes for cognitive psychology, and you can read a lot of this on your own. You don't necessarily need me to read all of this for you, but we have cognitive psychology, which is going to be another major focus for us because this actually does deal with things like memory, our ability to perceive the world around us, make the proper decision, which was obviously a major focus of Chapter 2. And then some others that are not going to be nearly as useful for us: experimental psychology, engineering psychology, IO psychology, personality psychology, educational psychology. But one we actually will spend some time talking about is this last one, social psychology, which again is the study of how people are influenced by the people around them. And of course, this will apply to everyone within a flight organization, not just the other members of your flight crew, but also people like air traffic control, your customers, your cabin crew, your supervisors, the CEO of the airline, etc., etc. Okay, so let's talk a little bit about cognitive psychology. Specifically, what we're focusing on here is the way in which our brains process information so that we can output the correct function and the correct action. So more specifically, cognitive psychology is going to focus on the way in which humans think and process information to produce responses. So we've actually learned quite a lot in this field, not only just through the application of the scientific method, but in doing so, we've teased out a lot of the specific pathways by which sensory inputs are processed, integrated, and translated into outgoing motor or visceral responses. So we'll talk about more of this in detail in future chapters, but for now, you can kind of think about it in very basic terms. Your brain and your body operate something like a computer. If you input something into your computer, if you input a command in your computer, your computer is capable of processing that information, then outputting the proper response. Okay, so if you hit Alt-Control-Delete, your computer is going to process that and then bring up your task manager. So that is the way your computer is programmed. You gave it an input and it gave you a response. So the human body is very much like that as well. And we actually know enough about how the human body operates that we have teased out the specific pathways by which this has occurred. So if we think about it in this regard, but we update it with some extra information, the sorts of inputs we are going to give ourselves and give our body are things like visual cues, the things that we see with our eyes, Tactile cues, the things that we feel with our hands. Auditory cues, the things that we hear with our ears. Olfactory cues, the things that we smell with our nose. And then another one that you may not have heard of before called proprioception. I believe your book calls this somatosensory inputs. So these are basically just cues coming from all over your body that help you to understand the position that your body is in. And given what we've talked about before with spatial disorientation, this one is going to end up being very important, and this is the type of input that can very easily be confused by your brain. So these sorts of inputs are going to be put into our major processing centers within the human body, which is going to be the tissue either of the brain or sometimes the spinal cord. So your brain and spinal cord make up what's called your central nervous system, and these are going to be the tissues and the organs that do all the information processing, the processing of complex information to decide on the appropriate response. There's not really another kind of tissue in the body that does this. Your heart can't do this, your liver can't do this, your muscle can't do this. It is your brain and spinal cord that are specifically designed so that they can receive incoming information, process it, and then give out the proper response. Something that we will learn in a future chapter is the nature of how these inputs stimulate what are called receptors in the body. So it takes a special kind of receptor activation for the light that we see to activate what we call photoreceptors, which are located in the retina of your eyes. Tactile cues involve activating specific receptors in your skin. Auditory receptor activation involves receptors that are located in your inner ear. Olfactory receptors, obviously, in your nasal cavity, and then proprioceptors are located everywhere. So there has to be a specific way by which these receptors are activated by these different stimuli. The stimuli being the light that we see, the things that we touch, the things that we hear, the things that we smell, and so on. Once these receptors are activated, a message is sent to the brain and to the spinal cord, and then once that information processing has occurred, an outgoing message goes from the brain and from the spinal cord to produce two major types of outputs. Either a motor response, which is a voluntary contraction of your skeletal muscles. So these are the muscles that allow you to move your hand, turn your head, chew your food, speak, etc., or visceral responses, which are the subconscious automatic reflexes that your body initiates, such as an increase in heart rate, a secretion of a hormone like insulin after you eat your food, the processes by which you digest your food. These are things that you don't actually have to focus on doing yourself. Your body will do this automatically. So in both cases, there is communication that is happening in the body. From the time the input activates a receptor, we are going to send messages to the brain and spinal cord, and then from the brain and from the spinal cord, and these messages are going to be traveling through nerves in the body, either through cranial nerves or through spinal nerves. So we will learn more about that in a future chapter. So we can actually look at a more complicated and astonishingly more accurate view of how this information processing works. So this is Wiccan's model of human information processing. So you can obviously see that there is a lot of complexity here. There is some filtering in terms of incoming stimuli, what gets converted to long-term memory, what actually sticks with us and what do we forget easily, how do we perceive the different types of stimuli, where is that information stored, where is that information even sent in the brain. So there's a lot going on here that we will address in the future, but basically what you should take from this is that the very fact that this is an accurate but astonishingly complex model should tell you that your brain is actually very capable and capable of very many things, But it also tells you that there's so many moving parts here that if there is a breakdown in conscious attention in any one of these aspects here, this can lead to the different kinds of errors that we discussed in chapter 2. There is a lot going on in terms of accessing things like the things that you have learned in training, the things that you have committed to memory. So any kind of breakdown in any of these pathways can lead to problems and mistakes and errors. So here's a breakdown of some of the major human senses that are involved in piloting an aircraft. A lot of these are going to be a little bit self-explanatory. So I talked about vision. This involves photoreceptors in the retina of your eyes that are stimulated by the incident light that enters into your eyes. So this will involve communication messages being sent through the optic nerve into your brain. So that's one of the cranial nerves that I mentioned. The things that you see are transmitted to the brain via the optic nerve. For audition, which is your sense of hearing, this happens in your inner ear in a sensory organ called the cochlea. The hair cells in your inner ear are stimulated by vibrations in the air around you. And this information is sent via the vestibulocochlear nerve. I know it says auditory nerve there, but that's not really the correct term for it. It's called the vestibulocochlear nerve. For tactile cutaneous sense of touch, there are different kinds of receptors all throughout the skin of your body, things that detect pressure, temperature, pain. The pressure sensors are called mechanoreceptors, the temperature receptors are called thermoreceptors, and the pain receptors are called nociceptors. So these different kinds of receptors are distributed all throughout the skin, and activation of any of those receptors by the things that you touch, or things that are hot, or things that are cold, or things that hurt, those will send messages through spinal nerves into the spinal cord and then up the spinal cord to be processed in the brain. For olfaction, this is your sense of smell, so you have olfactory receptors located in the nasal cavity, and this information will be transmitted through the olfactory nerve, another cranial nerve, in addition to the optic nerve and the vestibulocochlear nerve. Your vestibular senses, which are going to be very important, this regulates your sense of balance and equilibrium. This is also happening in your inner ear, except it's not happening in the cochlea. It's happening in what's called your vestibular apparatus, which includes the semicircular canals and a couple of other sensory organs there as well. We're going to learn in the future that this process involves hair receptors as well, very similar to audition, and that information will also be transmitted through the vestibulocochlear nerve. And then you have your somatosensory or proprioceptor sensations. This is your sense of overall position and movement of body parts in relation to one another. Okay, so we're nearly done. Let's wrap up by talking a little bit about social psychology. Social psychology is going to entail how people's thoughts and behaviors are influenced by others. So we talked about some of these ideas in chapter 2 when we were talking about organizational perspectives and the different types of behaviors that can encourage routine violations. The example we gave is that if an airline provides flight crews with some kind of reward for always operating their flights on time and on schedule, then that could encourage routine violations in the future if conditions present themselves that, well, it'd probably be best if we delayed this flight. It would be safer if we delayed this flight. Well, if social interactions are causing you to think, oh, well, I mean, we could probably get away with not de-icing the wings. We really need to get this flight off in time so that we can collect our reward. That's a routine violation, and that is a social psychological issue. But the issue here is that social influences are very difficult to scientifically control for. So airlines and other flight organizations try to mitigate something that's so hard to control for by standardizing flight operations with things like operating procedures and checklists so that we can remove potential negative social influences. If everybody is trained to always follow a certain procedure or run through a checklist, that mitigates or minimizes the potential of having negative social interactions that could actually cause risk to the flight. So there are definite benefits to social interactions and their effects on the human psyche. So it's a good thing to be around other people. That's a good thing. It's never not a good thing to be around other people. We were designed to be around other people. But the negative aspect here is that group behavior can be detrimental to flight operations. So a quick definition, a crewed flight deck by definition includes at least a captain and a first officer. Often it will include maybe a flight engineer or someone else, but a crewed flight deck at minimum has to have a captain and a first officer. So crew resource management, which we've talked about before, these techniques help to standardize group behavior. Again, things like operating procedures, checklists. We try to standardize group behavior in crewed flight decks to make sure that we minimize the potential of negative social influence. So a good example of this is the sterile cockpit rule. No chit-chat, no non-essential activities if you're below a certain altitude, because we've learned before that operations that occur at low altitude are by far the most dangerous and most mistake-ridden parts of a flight operation. So that is the part of the flight operation we want to try to minimize the risk of bad social influence. Okay, so let's wrap up with some concluding remarks, because this wraps up the first unit of the textbook. And starting with chapter 4, we are really going to start getting into some human physiology. So let's take a moment to take stock of what we've learned and make sure that we enter into the next part of this class with the proper perspective. In chapter 1, we learned that human error is the source of most aviation accidents. In chapter 2, we learned about the different kinds of human errors and where they might come from, and we came to accept their ultimate inevitability. We are human. We are going to make mistakes. We are going to make errors. In this chapter, we have introduced the multifaceted discipline of human factors, and moving forward, we are going to strive to understand the human mind and the human body to better appreciate our own limitations so that we can fly more safely. You will fly more safely. I have told you before, I am not actually a pilot myself, but my goal in being your instructor this semester is to teach you everything I know about the human body, or at least as much as you need to know, so that you can understand the basics of how the human body works, how it is limited, so that you can fly your airplanes and have a very long and very happy and very healthy career. Okay, that is going to wrap up chapter 3. I appreciate your attention. In the next chapter, we are going to start actually getting into some fun human physiology, and we will start looking at the effects of altitude on the human body and the state of hypoxia that we mentioned in this chapter.